Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from Scratch in Go, where we dive into the bare bones of what is the neural network is, and we are implementing everything in a Go. To do this, I'm using this neural networks from Scratch in Python book, but again, as you can guess from the name, I'm not going to copy-paste all of the code from the book, and I'm trying to, I diving into what it does and implementing everything with the Go. So far, I've been using only standard library and the library that's called GoNum, which is, I would say, in some way an alternative to the NumPy, not that powerful and not that many features. Maybe I don't know all of them yet, but it provides working with the matrices in a more, in a faster and optimal way. So in a previous video, I managed to implement the categorical cross-entropy loss, and I've been checking after the video the code a little bit, and I wrote this to do because I implemented only this branch, and it's where the target, where is it? This one, target array consists of numbers of the categories, but there is another way to provide it, and it's array of arrays, where the inside array consists from the same number of values as the classes, and only one value is 1 and the rest is 0. So for example, in that case, for example, for the class equals 2, for example, in a one-dimensional way, like in this one, it will have it will be the array of the int values with 0, 1, 2, 0, 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. But in the two-dimensional, it will be array of arrays with the 3 elements. And for example, if in one case it should be the 0, then here it will be 1, here it will be 0, 0, and so on. And I'm not sure. I mean, I'm thinking maybe I should implement right now, or maybe I should leave it as it is for now. I'm not sure at which point we will need it. The problem that, not really, the problem that Golang doesn't have the function overload. The function overload is a way to write the same function, but with the different arguments, and based on the argument that you provide, the specific function will be chosen. It's not the case for the Go, as I learned, and one of the ways for me is to replace the standard Go array with dense. Maybe they have something like vector, int vector, because this uses the blast with float values inside, but I don't need floats, I need integer value here. But let's see, I'm leaving the to-do for now, and if I will need to have both, because I always can, go from one representation to another to calculate the loss. So I will try to stick with array of the classes, but if in some case we will need it, then I don't know, maybe for some batch processing it will be way efficient to do like this. So we'll see. The only leftover for the chapter 5, that is calculating network error with loss, there is only one thing is missing before we can go to the next chapter, and it's accuracy calculation. So while loss is a useful metric for optimizing the model, the metric commonly used in the practice along with loss is accuracy. So we have a loss and accuracy, which describes how often the largest the largest confidence is the correct class in terms of the fraction. Conveniently, we can reuse existing variable definition to calculate the accuracy metric. We'll use the argmax values from the softmax output and then compare these to the targets. This is as simple as doing. Note that we simply modified the softmax outputs for the purpose of this example. Okay, so we have known that we slightly modified for the purpose of this example. Okay. So we have the softmax output, which is our prediction. We have the class, which is the target. Then we need to calculate argmax for the softmax on the axis 1. So I believe so that should return what it should return. Okay, first of all, what is the softmax? What is the argmax? And I think return the indexes of the maximum value. So it will return the index. Calculate. Right. I'm curious that it returns indexes, not the values itself. If targets are one hot encoded, convert them. Oh, so we calculate the mean. Okay, so idea that we taking the max value for each row. We're taking the index, and in our case, the index will define the class. So basically that we taking the predicted classes and we converting them from the array of arrays with the probabilities. We converting them into. How is the different? Yeah, okay, it's different. Okay, so we'll take the indexes of the predictions. So that here we'll have the predicted classes. Then we have the class targets, which is our target. And then we need to calculate the mean of how accurate it is. And there is a Boolean expression, and there is a comment that true evaluates into 1 and false into 0. So for all of the correct predictions, we'll have 1 value. For incorrect predictions, we will have the 0 value, and then we take in the mean. And the mean is compute the arithmetic mean along the specified axis. Well, the arithmetic mean is the sum of the elements along the axis divided by the number of the axis. So basically we need to find the average number. Okay, so we have loss. Okay, I will leave it in the loss folder for now. In this. Yeah, I think I will just make it to the function. So func. Calculate accuracy and I have some inconsistencies with the name, but okay, I will go the same. It's actually not the output, it's yeah, methods undefined. Do I need math? Probably not. And it returns value. Right? Okay, so the first thing we need to write an argmax implementation. So we go into okay. So we're going over the rows, we take in row values, and that will be prediction row, what's called row view, right? What returns? Oh yeah, basically we actually has a vector. Row view returns I. It's a column vector, but by C. Row view returns row I of the matrix data represented as column vector. And then, okay, I have the row values. Then I need values. I think no. Can I take the row? I think I should be able to row. Oh, I need this one. Row view. Row. Then plots sum, and we get the row values. No. What am I doing? I need to find the max. I need to find the max index. Right. Max index, not sure if what's max. Maybe this one. Max IDX return the index of the maximum value in the input slice. If several entries have the maximum value, the first, okay, it panics if S is 0. Yeah, but I have the max value, and now I have And I need prediction classes, which well, we'll make it plot 64 by len of y, because they should be the same. And prediction classes, it should be max index, right? So what we have this one. We have the list of the predicted classes. We're not going to do this yet, for the same reason as I talked in the loss. And I need to calculate the accuracy. So I'm wondering, is it really that GoNum doesn't have this? GoNum, okay. The mean of the probability distribution, but I want to calculate the mean. Okay, I can't find, I mean, I have a feeling that this, the mean should be available, but okay, let's just implement it in, simple way. Or range, what I'm checking, prediction classes, right? Well, do Go have the ternary operator? Golang, how it's called? Single line condition. There is if yeah, Golang is really simple. As the comment mentioned, Go doesn't hold ternary one-liner. The shortest form I can think of is... Okay. Then we'll do the classic way. If predicted class equals to target classes. Target classes I want like this. Then sum plus 1. And what we return sum plot from sum divided by plot 64 by the len target classes, right? That should calculate the accuracy, right? So print what do I mean? It's from it's loss, right? But I have loss. Yes. Like this. Softmax output and target classes. What do you mean it's undefined? Okay. Categorical loss. Okay, so we have our accuracy, which is pretty low. So it's like, 9% of the correct predictions. Okay, but okay. Okay, then, and if you know where I'm missing the mean value for the go num, just please let me know. I'm sure there are lots of the other packages that could provide it, but I'm just trying not to add too many dependencies. But the good news is that we have interesting. Here it says 30. Also, we can add the following to the end of our full script above the accuracy. So we have the predictions, accuracy, well, interesting that they have the accuracy higher. So then it's a question, did I implemented something wrong, or they have a little bit different data? Let's debug it just to be sure. Okay, so we have the raw values. Okay, we have the max index 0. Well, values are the same. And okay, then, well, for example, this one is different. So the max index 2, then, okay, so let's try this. Not this one. Well, okay, we have the predictions, I mean the predicted classes, and we have how many? 300. And what about the target class? Yeah, same, 300. Okay, then if they equal, right? Interesting. Will it? No. Cannot find symbol value for y. No? Oh, maybe like this. Oh yeah, it's 2. Okay. So then we do like this, and we should see we have the sum. So I mean, the model calculated correctly only 42 classes out of the out of the 300. Okay. Okay, I would assume that that's just my distribution of the data that I generated, and this is just my model. Maybe here it has better initial weights. So right now we go into the next chapter, which is introducing optimizations, and let's see how many things we'll be able to check together, because I see this line, and it means that again I will need to implement some data generation like I did with the spiral data, like this one. I have the data sets and I have this function that generates. So let's see, maybe I will need to implement something different again. Now that the neural network is built, oh yeah, we actually have the neural network. I mean, I will just do this accuracy, just, this is the model, right? We have inputs, we have first layer, we have the second layer, and let's where I can draw. Okay, I want to draw something. So we have, if we take a look at the input, we have 300 points by 2. I mean, we have 300 samples, and each sample is the 2 values. So and if we take a look at the first layer, we have number of inputs and number of neurons. So for us it looks like, so this is our input. Then we have the first layer, which is this one, right? Then we have the second layer, which has 3 inputs because of the previous layer, and we have 3 outputs. And I'm not sure how to draw this, because, well, do I have the text? No. Yeah. So this is inputs. This is the layer 1. I mean, in the book, that was called the second layer, But the thing is that maybe because we do like this output. The difference is that can I change the style? Well, okay. So we have input connected to the first, then we have this connected to this one, and we get the output, and then we pass it through the softmax somewhere here. Softmax, right? And then we can get the output. So in that case, yeah, probably that would be the correct representation, because we're not taking the data out of the layer directly, we're passing it through the softmax, right? We're passing the stuff from the layer 2 through the softmax to get an actual output. Yeah, I think that's more correct. Okay. And this is our neural network. Now that the neural network is built, able to have data pass through it and capable of calculating the loss, the next step is to determine how to adjust the weights and biases to decrease the loss. So we will go in the batches. Like for example, we took some data, we pass it through the neural network, we calculated, well, in our case, we calculated the predicted classes, we calculate the loss and the accuracy, and I'm still, trying to put it in my hand. So the accuracy is the value of how wrong the model, and the loss is the value of how far away model from being correct, something like this. Find an intelligent way to adjust neurons' inputs, weights, and biases to minimize loss is the main difficulty of the neural networks. Well, I guess for the train part it is, but yeah. The first option one might think of is randomly changing the weights, checking the loss, and repeating this until happy with the lowest loss found. To see this in action, we will use a simpler dataset than we have been working with so far. Using the previously created code up to this point, we can use this new dataset with a simple neural network. Okay, so we'll create a different dataset, we'll create a different neural network that that's interesting. Okay, so the first thing, I need to find this one. Because I'm going to implement. So the first thing, I need to implement this. Test it again. I think I have the scatter data. Yeah, that should work. That should work, yes. Yes, and probably that will be enough for today's video. So let's go. We have scatter data. Okay, I will put it into the different file. Okay. Okay. Oh yeah, I have the random, so this is why the accuracy is different. Okay, yeah, then it makes sense. Okay, they have the scatter data in a different one. I have spiral, then I have vertical, and I think I will take from here. One vertical data up to what it takes. It takes the number of the samples and the classes and returns two-dimensional array and one-dimensional array, right? So that okay, let's take a look at the code. Okay, it looks much simpler and it looks like I can copy the spiral code because the only thing is different is the actual computation of the x value. And for example, I don't need R and T now, right? Right. By the way, what is this? Translate slide object to concatenate along the second x. Okay, I don't need this. So for y we still have the class number. So then we change in this, and it's random number from okay, random values in a given shape. Create an array of the given shape and play it with the random numbers from a uniform distribution over 0 to 1. Okay, and this one... Norm quotes is referred to as normally distributed in a range of... But do I have something like go random between 0 and 1? Okay, if I want to have it as 0 from 1, looks like I need to find or implement my way. Random value. Mean value 1, max 100, then value rand int returns as an int a non-negative pseudo number in the half open interval. Okay, so actually just do like this, and then I return divided by this. Because that will be okay. Oh, it's in a spiral, but okay. No, not this one, right? Okay, so I need the random value from okay, so we're taking the super small, right? So it generates, okay, we pass in the number of samples, so it can give a shape. So for example, we're passing 3, that it will generate 3 values, right? And it will generate between 0 and 1, but we do it manually. And then once it generated, so we can take random value multiplied by 0.1 plus class number divided by 3. Yes. And this one, we're taking again the random value multiplied by 0.1 plus half. Okay, I don't need this, I don't need this. So that's the vertical data. Okay, I don't need this. Okay, let's try to use it. I'm taking the data and nothing from data set vertical data, and I'm taking the again 103 classes. Then I do scatter, right? Data and the class counts. What do you mean undefined data? Ah, Okay. Open points. Okay. They kind of a little bit closer as in the example. So maybe the randomization is a little bit different, but yeah, this one is closer to this one, this one. Yeah, but from the code, it still should shift it a little bit. But anyway. Okay, we implemented this one. Then looks like I need to implement, I'm checking the recording in 50 minutes. But I will cut some of the, okay, let's write another another model. Let's call it run simple model. So we take in this target classes. Yep. Okay, I have the same problem here. Run simple model. Yeah, they are not used, I know. Then we create how many? 2? I think that's the same, right? So we have layers 2 by 3. We have again the activation function. We have the second 3 by 3. We have the loss, same. And then create some variables to track the best loss and associated weights and biases. Okay, first let me test that it works. Let's not. And define inputs. What do you mean? And define inputs. That should work, right? Okay. Using the previously created code up, at this point we can use this new dataset with a simple neural network. The only difference that right now we're using the vertical, but we still have the same, well, actually not the same distribution. Okay. Interesting that for the last class it's kind of the same. Maybe there is an error here, I don't know. Because it's consistently for the last class. But okay. Accuracy 0. Nice. Okay, and then we're going to create some variables to track the best loss and associated weights and biases. And then looks like we're going to do actual optimization and the training. And I'm going to leave it for tomorrow. Thank you for watching, and I see you tomorrow. Bye bye.